проверю, оно идет, не идет. Раз, раз.
А, это надо надеть, да? Так. Так, ну что, надо начинать. Еще пару минут подождем. Ой, что такое-то? Так, ну что, надо начинать. Я чувствую, что сильно больше народу не будет. Вася собирался коллеги найти, слушайте. Так, а меня уже записывают. Well, let's start the lecture. I recall that we discussed the spectral sequence of a double complex. A double complex is the set of a abelian group indexed by two integral indices with a pair of differentials. The first decreases the first gradient, the second differential 2 primes decreases the second gradient. And I prefer the convention that these differentials anti-commute. Then we can arrange this double complex to a total complex by taking sums over diagonals. I assume that these sums are always finite. For instance, it is true when we are always in the first quarter, but sometimes other situations also appear. And we have total differential, which is just d prime plus d2 primes. Okay, and then our goal, the goal of the spectral sequence is to assume that we more or less understand homology with respect to these two differentials, and we want to pass to study the homology of the total complex. And I recall how homology classes of total complex looks like. A homology class is a set of elements, not a homology class, but a cycle is a set of elements which are situated on a diagonal with the following condition, that the sum of, if we can, here we have P, here we have Q, and we have D prime and D two primes. And here these two things should sum up to 0. And the same in all other cases. Then this set of elements, their sum is a cycle in the total complex. And similarly, it is a boundary if there exists such set of elements here, such that these elements, if we compute all these differentials, they again sum up to those elements which were here. So this is general picture. And also I recall that we introduced filtration in S plus teeth homology of this total complex. It is convenient to index this by two indices. So the sum of these indexes is just the number of a homology group. And these are those homology classes which can be represented by cycles lying in semiplane P less or equal to S. So then this point has coordinates st, and a homology class lies in this subgroup if and only if it can be represented by such element that we have zeros in all places on the right from this line. And on the left, we can have arbitrary elements. And I want to stress that this is only the definition of this group is that there exists such representative. Of course, there can be also representatives where we have not zeros here. The same class, adding some boundary to it, we can obtain that we have not zeros here. But a class belongs to here if and only if it can be represented so that we have zeros in all these places. Of course, this group is the larger S is, the larger this subgroup is. So we have the smallest one is F0T. It is just F0. If we consider the group Hn, then we have F0n, F1n minus 1. All inclusions are non-strict, of course. And the largest one is Fn0. And this is just the whole homology group. This is for the case of the first quarter spectral sequence, but in other cases, just indices may differ. And last time we have, now I want to recall what we have discussed during the last lecture. First of all, we introduced subgroups in this group DPQ. We introduced subgroups, two series of subgroups, cycles and boundaries. So we introduced such series of subgroups that we have introduced two series of subgroups, B and Z. So this was just the kernel of differential d2 primes, and this was just image of differential d2 prime. And of course, when I write kernel, I mean that, okay, d2 primes has its own kernel in any cell here, and I mean the kernel in cell PQ, of course. Okay, and also I would like to recall the definitions of all these groups. So the definition of the group Z here, Z, if I will want to consider the group Z PQR, I need to consider all y's in the cell with coordinates PQ with the following property. I prefer to draw it for r equal to 3. I want these cells to be not very small. So we need to have the definition is that y belongs to here if and only if there exist okay, let it be. There exists element. On the last lecture, I enumerate these elements by their coordinates, y, p, q here. Today, it will be more convenient to me to use another enumeration. I just begin, this initial y will be the same as y0. And here I begin them to enumerate starting from the last one is y r minus 1. So we have r boxes here. And the condition is that for this element is given, but all other elements, we want that such elements exist, such that here they sum up to 0 in all these places, and here it also goes to 0. Well, so this is exactly the condition that y belongs to this z if and only if there exists such sequence of yi's. And similarly, y belongs to b rpq if and only if there exists here again. I have this box with coordinates pq, and here is y. If and only if there exist elements here, an element here, and so on. And again, I have r boxes on this diagonal. And the condition is that here they sum up to y, here they sum up to 0, here they sum up to 0, and finally this also goes to 0 here. Well, this is exactly the definition which we discussed yesterday. Here, in this case, I even do not need any notation, but here I will use this notation later. And during the last lecture, we discussed that, first of all, we have such inclusions, but this is more or less obvious. And second, that the final term, the limit term, but we consider only those cases when we have actually no limit, when everything finishes on a finite step. Then the limit term is closely related to this filtration. Namely, this group E infinity PQ, which is by definition Z infinity PQ, quotient by B infinity PQ, this group is canonically isomorphic to the quotient group of consecutive elements of this filtration. It is FPQ quotient by F P minus 1 Q plus 1. So if we understand the last term, then, and the mapping from left to right is just we take this representative of homology class and assign on this this entry to it, the entry in this box, and we get into the ZPQ infinity. So there is such natural isomorphism. So if we manage to compute the last term, then we arrive to some understanding of homology, not to complete understanding. Namely, we do not know the group itself, but we know its consecutive factor quotients. And also, we start with a very well-known thing. Generally, I recall that ERPQ is by definition the quotient of ZRPQ by BRPQ. So when R decreases, then ZRPQ becomes smaller and BRPQ becomes greater. So we always take the smaller and smaller and smaller group and take quotient by bigger and bigger and bigger subgroup of it. So our group becomes smaller, smaller, and smaller in two senses. We, at any stage, we take a subgroup and take some additional quotient. Okay, and we start with groups which we assume that we know. H1PQ is just the kernel of, the kernel of differential quotient by the image of differential. It is just the homology of our complex with respect to differential D2 primes. So, okay, that's the point at which we stopped last time. And now let us go further. To go further, we need, now we need to go along a way from this group to that groups. We understand that what is in the beginning, we know these groups, and what are at the end, they are closely related to what we want. So now the next step is that we would like the basic object is differential dr, which goes from the rth term of spectral sequence is the set of all groups ER with different indices PQ. So on each step, we have such table of groups. We have E1 we know, then we want to pass to E2, to E3, and so on. So on rth page, on rth term, we would like to have differential which goes from group ERPQ to the group with the same number R on the same term. And here we want to have P minus R, Q plus R minus 1. So it decreases the first gradient by R and increases the second gradient by R minus 1. The total gradient is decreased by 1, so as usually in homology, by homology differentials. Okay, and with this definition of groups Z and B, it is very easy to see the definition of this dr. So, both these groups are quotient groups. Yes. So, of course, I first want to define this homomorphism on the numerator group, And then I will check that this belongs to the kernel, so it is well defined on the quotient. So let us start with, I introduce, this is standard notation, this is not non-standard, this is just for a moment. This is very auxiliary, very auxiliary object. I first would like to define this homomorphism on the group Z, and then check that it is well defined. So, and here I also have this such quotient. This is exactly what we need, this group. Okay, how to define this? Well, very easy. We just need to look on this picture. Assume that we have an element y in Z PQR. Then, by definition of this group, there exists elements y with indices here, so that, okay, these differentials sum up to 0. But we have no restrictions to this differential. So by definition, the image here is delta r of y. So we can take d prime. So by definition, dr of y is the image here. So it is d prime of y r minus 1.
Why is it unique?
Oh, yes, that's what we want to. So what we need to check. First of all, we need to check. Okay, this is not very good notation. This element belongs to the group. This box has this pair of coordinates: p minus r, q plus r minus 1. That's okay. But this is an element of the group D with these numbers. First of all, we need to check that it actually belongs to Z. Second, we need to check that up to an element of this group, actually as an element of this group of Z, it is not well defined. It depends on this choice. But we will check that up to an element of that group, it is independent of the choice of y's. Let us do it step by step. First thing we need to check that this element actually belongs to Z. So first, let us check that d prime y r minus 1 belongs to Z with these indices zr, p minus r, q plus r minus 1. Well, that's rather easy. The matter is that, in fact, it belongs even to Z infinity. With the same numbers. Actually, it belongs to all groups Z. Let us check this. Okay. I want to draw this last step. So I have y r minus 1. Here I have I want it to be greater. Y r minus 1. Here I have this d prime y r minus 1. And what I know that here this is d prime, and d2 prime of r minus 1 is the same as d prime of y r minus 2. Okay, they sum up to 0. Okay, what can we say about this element? First of all, I claim that it goes to 0 here. look, if we go, if we apply d2 prime here, if we apply, go in this way, up to sign, I don't want to worry about sign. It is the same as we go by in this way. Again, up to sign, it is the same as we go this way. And of course, well, I forget to write down today, but of course, each differential squared is 0. So if we go like this, we get 0. So we know that this element goes to 0 here, but it is obviously goes to 0 here as well, just twice d prime. So this element is a true cycle of, it is alone a true cycle of the total complex. So once we would like to check that this element belongs to Z with any number, we just need to choose zeros in all these, for these auxiliary elements, we just can take zeros, and the condition is satisfied. So it obviously belongs to any group Z, just with trivial choice of this auxiliary sequence of elements. So this is easy. Well, now we want to, this was first check. Second check is that, okay, we have indeterminacy of this element. This auxiliary sequence of yi's is not unique. So we may choose various sequences of such kind, and this element is not unique. But the second claim is that the indeterminacy of this delta r of y lies in this group. So if we choose another sequence of such kind, we just get an element which differs from the previous one by an element of this group. So let's fix this. The indeterminacy of delta r of y lies in B with these parameters. Actually, it is directly from definition. Look, suppose that we have two sequences, one sequence yi's, and the second sequence yi's with primes, which both for the same y, of course. Well, but then if we take differences here, and here also, then we have true zero here. We just take zeros of all these sequences. And then, look, what we see here is exactly such sequence. We can, here we have only r minus 1 boxes, but we also have 0. We put 0 here. And this is exactly this sequence for the element d prime of y r minus 1. So this is we get exactly into this definition. So this is just by adding 0 here. So we have checked this one. So this delta r is well defined. Now we actually have well defined delta r. Now we would like to study the kernel and the image of this delta r. And the claim is, let us start with the kernel. I erase this one. So now point 3, I claim that the kernel of this delta R is exactly Z with the next ZR plus 1. I want to restore here the initial situation. The initial situation was like that. We have R here, it goes to 0, then we have Y1, Y2, and so on, YR minus 1. Okay, I claim that the image is just the next, the kernel is just the next group Z. Why? Oh, sorry, I forget to switch off the. This is slightly non-trivial. This is the only slightly non-trivial check. Let us understand that this inclusion is obvious, but the opposite one we need some work. Why this is obvious? Okay, if an element belongs to the next group Z, then by definition we can check this sequence one step more. By definition, we have here YR, so that they sum up to 0 up to this point here also. But then we see that delta R of YR minus 1, it is the same as delta R of Y is represented by this element by definition. But it is the same as D2 primes up to sign, minus D2 primes of YR. And then it belongs to B1 just by definition. The image of D2 primes of B1 with corresponding indices, and hence it also belongs to BR. So it is not important for us. So it is hence it is 0 in our group ER. Okay, this is easy inclusion. Now let us, this was point A. Now B, we would like to prove opposite inclusion. So suppose that an element, now we do not have this YR, but suppose that an element Y lies in the kernel of delta R. What does it mean? This means that this element D prime of YR minus 1, it is not true that it is 0. It is true that the matter is that we have our map is not to this group, but to the quotient. So if delta R of Y is 0, this means that this element belongs to the corresponding group B. This means that D prime of Y R minus 1 belongs to the group B R with these indices. But, now we need to look on the definition of this group B. What does it mean that it belongs to the group B? It means that we can choose, for this element, we can choose element like that, which satisfies this condition. let us denote let us denote these elements. Okay, these elements, we must have R boxes here, starting from this one. So they are from here up to here, up to this one. Without that, these are boxes for this element. They are here. So we must have elements which I denote by Z, R minus 1 and ZR, which satisfy this condition for that element. So what does it mean? This means that Z1 goes to 0 here. Here these Z's sum up to 0, and at the last points this Z sum up to d prime of y. But now let us change these y's by z's. We choose another sequence. We choose yi's primes, r yi minus zi. Then we get, they again satisfy condition that we have zeros in all these points. But what we have here? We cannot do the same trick here. So we obtain, without the, for these new elements, we obtain that d prime of y r minus 1 prime is just d2 prime zr. Hence, it is again in the group B1 with these numbers, and so in BR. So it is actually 0. This is the opposite conclusion. We started with that the element lies in this kernel. Oh, sorry. Oh. At the very last step, I forget what I prove. Okay. Once this is satisfied, I have this sequence. I just take this ZR for YR. I just take YR prime equals to Z only to minus ZR. And that's the required sequence of length R plus 1. Well, so now we have proved the inclusion. We started from this and we finished with a sequence of length R plus 1. Well, that's the kernel. And the final thing which we need, it is the image. Yes, at this point, before thinking about the image, let us make one observation, that now we see that the dr is well defined. Now, in particular, once this is the group Z with the next number R plus 1, then in particular, this kernel contains any group B, actually even B infinity. In particular, it contains BR. So we can take the quotient and we get a well-defined. So what we have already proved, it follows from it that dr is well-defined. And now we want to find the image of dr. Of course, the image of dr is exactly as the image of delta r. It doesn't matter which of them we consider. So the final check we need that image of dr, which is the same as image of delta r, this is obvious. What we need to check? We need to check that this is the following. This is the quotient of BR plus 1 over BR. Well, indices, of course, are always this pair, but so we see that this BR, we have a greater group BR plus 1. And this is exactly this quotient. Well, let us check this. Again, one inclusion is very trivial, and the other, oh, in this case, so both inclusions are trivial, but okay, let us check them. So let us check with this inclusion. Suppose that an element lies in the image of, I would like to erase once more. Suppose that an element lies in the image of, we have y, y1, y2, etc., yr minus 1, and it goes to delta prime, d prime of yr minus 1. Well, suppose that we have this element which is in the image of delta of dr. What can we say? I'm sorry. I once more. Well. We can say that, well, this is in the image, so well, that's very easy. All these sum up to 0, yes? And here it goes to here. So let us write down 0 here. And we have exactly those sequence for this element with r plus 1 boxes. So this inclusion is immediate. If we take any sequence of such kind, then delta prime of yr minus 1 immediately belongs to the group B with the corresponding index. Okay, so we need only to prove the opposite inclusion. The opposite inclusion, assume that this element belongs to BR plus 1. Yes? What does it mean? Sorry. Not this element. At this moment, we do not have any y. Let us just start with any element of BR plus 1. Well, any element of BR plus 1 is the same as, let it be Z. And let it be BR plus 1. I would like to study an element of BR plus 1 with indices P minus R, Q plus R minus 1. Okay? I am interested in this group. So this Z is here, so this cell has these coordinates, P minus R and Q plus R minus 1. What does it mean that it belongs to here? It means that there is such picture, but with R+1 boxes, since we have R+1 here. Okay, and now I claim that just I take this sequence and I denote this by y. Then, if I go along this line, I obtain almost that z equals dr of y. Almost, because I also have something here. Let it be x. What I obtain, if I choose this sequence for y, then I get yr minus 1 here. So I get that z equals d prime of yr minus 1 plus d2 primes of this x. But okay, what we see, this one obviously belongs to the image, but this one belongs to, again, this one belongs to B1. So it is actually 0 in the group we are interested in. So we see that Z itself belongs to the image. That's all. We have constructed such differentials. So now let us sum up what we understand. We have constructed these differentials. The differential has by degree minus r minus 1. So it decreases the first coordinate by r and increases the second by r minus 1. And what we see that its kernel, since kernel of delta r is like that, it immediately follows that the kernel of dr of course, it follows that kernel of dr is exactly this quotient. Well, dr is just obtained from delta r by taking quotient by the group B, which we have proved that this group is in the kernel of. So, okay. We see that we have constructed such element that kernel is like that and image is like that. But, well, now let us recall that we have not only single such differential, but we have such differential for any cell PQ. And now let us consider two differentials which okay, let us consider the cell ERPQ and consider the differential which goes to it and the differential which starts from it. The differential which starts from it goes to this group ERP minus RQ plus R minus 1. Yes? Let us for a moment introduce this additional these additional indices to show from which group the differential goes. And the previous differential is from P plus R, Q minus R plus 1, and it goes here, and it is differential with P plus R, Q minus R plus 1. Okay, and what we have proved? First of all, we know that the kernel of this one, kernel of drPQ, it is by definition, not by definition, but as we have proved, it is ZR plus 1 PQ quotient by BR PQ. But what is the image of that differential? well, this is the image of differential which goes from cell PQ. But if we would like to obtain differential which goes to cell PQ, then we have the same result, but here we have a pair of indices PQ. So we have that image differential of this differential is BR plus 1 PQ quotient by BR PQ. And of course, from this, we immediately see that the kernel up to the image is just the quotient of ZR plus 1 by BR plus 1. It follows immediately that this kernel of differential by image of differential is exactly ER plus 1. So is exactly the next term of the spectral sequence. Of course, further, we never will write these additional indices, and we just say that R plus 1 term of spectral sequence is the quotient of the kernel of dr by the image of dr. Okay, we have proved this fact. And actually, I would like to stress that, in fact, the only ideological part is that we consider such sequences and that we introduce dr as, well, this is the only ideological part. All other things are just direct check. We have not, no check here was complicated. Just we check step by step all properties. Well, and so, well, this means that R plus 1 step is homology of rth step by this differential dr. So the general picture is like that. That we take the first, the first term is given by just homology along D2 primes. Then we consequently consecutive differentials we have, and on each step we take the homology with respect to these differentials, and finally we arrive to something which is closely related to homology of the double complex. Well, that's the general situation with double complex. I want to say just one. I want to stop for a moment just on one important thing, that okay, higher differentials of spectral sequence are usually not accessible. Usually it is rather difficult to work with them. But first of all, in topology they are usually very inaccessible. Higher
differentials is drs with the big r?
Yes, drs with r greater than 1, in fact. So we need to build such sequences, but in group situation, in purely algebraic situation, we sometimes can build such sequences. For instance, with last lecture we saw something like that for pure braid groups, and but D1 is very easy object. Let us look on D1. When we are interested in D1, we have only one box here. So we have no these additional boxes. We have no additional choice. We just take D prime. So this is a very natural observation that D1 is just induced by D prime. It is not D prime itself. The matter is that Okay. Oh. Okay, what is E1 PQ? E1 PQ, as it is written there, is homology of the double complex with respect to D2 primes. So we have this we have such vertical lines, and in these vertical lines we take homology. But then we also had such these were D2 primes, and we took homology with respect to them, homology of each vertical column. And here we have homology of the previous vertical column. And these are D primes. And up to sign, these D primes are chain maps of chain complexes. So these vertical columns are chain complexes, and D primes are chain maps up to sign. But the signs are not important here. We can always pass to another convention if it is convenient to us. And what we see? We see that D prime, of course, if we have a chain map from one chain complex to another chain complex, then this chain map induce homomorphism in homology. And this is exactly our D1. So D1 is the homomorphism in homology of these vertical complexes induced by D prime. So in this situation, everything is very easy. That D2 primes, we first take homology with respect to D2 primes, then we induce differential D1 by D prime, take homology with respect to this different, and then we have some more complicated differentials, D2 and so on. But at least D1 is rather easy. Well, also I would like to it is convenient to well, such picture is rather useful. D1, this is D1. It goes by 1 to the left. D2 goes here. D3 goes here, and so on. So we have such just it is convenient to see on these by degrees of differentials. It is sometimes it is useful to understand that we can make one more step. In fact, we can start not with E1 but with E0. E1 is again homology with respect to D2 primes. So actually it is convenient sometimes it is convenient just to define E0 as the double complex itself, and D0 as D2 primes. Then the first page, the first term is the homology of zeroth term by D0, and then as before. Okay, and the last thing which I want to say about, not the last, one more thing which I want to say about this, that, okay, sometimes we have not decreasing differentials, but increasing differentials, gradient increasing differentials. For instance, when we work with cohomology, of course, then differential increase gradient. The situation of increasing differentials can be transformed to the situation of gradient decreasing differentials just by reversing the sign of these indices. Okay, if we have so if we have, then in this situation indices are usually written as upper indices. If we have such double complex with gradient increasing differential, so now let it be delta. Delta prime increases first gradient, and delta 2 primes increases the second gradient. Then we can, just by reversing the signs, we can reduce the situation to the previous one, but it is more convenient not to inverse the signs, but just, well, then everything is the same. The only thing is that instead of decreasing differentials here, in cohomological situation, we have the differential dr, which has gradient which increases the first gradient by r and decreases the second by r minus 1. Everything the same up to reversion of signs. So from, in this situation, the number of term is written as below index, and here we have pq, and it goes to er p plus r q minus r plus 1. And that's the only difference. Everything, all things are the same as before. Yes. So in this situation, the differentials go like that. This is d1, this is d2 by 2 minus 1, this is d3, and so on. Well, and another important note is the following, that, well, okay, in the original definition of the double complex, it is not important with decreasing gradient or increasing gradient, any of them. In the original definition, of course, d prime and d2 primes have the same roles. They are completely symmetric to each other. But in all our construction, they are not. We choose one of them for d0 and the second one for d1. And this is our choice. So in fact, with any double complex, there are two, not one, but two spectral sequences. Both go to some filtrations in homology of the total complex, but, well, they differ just by reversing the roles of indices p and q. But they are completely different, and actually they not only different, but they go to different filtration. They correspond to different filtration in the homology of total complex. In one situation, we take filtration is by those classes which can be represented to the left from some line, so in some line p equals to s. Yes? But in the second situation, of course, unfortunately I have no color chalks. In the second situation, the filtration is by such those classes which can be represented below some line. Of course, these two filtrations are not related to each other in any way. So they are completely different, but it is important to understand that we have two spectral sequences associated with any double complex. And now this note will be important for us in understanding the Hochschild-Serre spectral sequence. Oh, but before, well, I almost forget about that. Actually, the spectral sequences are useful in many situations, but the most useful thing is multiplication of spectral sequence. And now let us discuss this aspect of our study. But okay, multiplicative structures in spectral sequences exist only if there are some multiplicative structures in the initial bigraded complex. So, okay, we have plenty of situations when we have multiplicative structures in some chain complexes. But it is more often that we have them in co-chain complexes. But, though there exist situations when we have them in chain complexes, but still it is more usual to have multiplicative structures in co-chain complexes. But also we can have such multiplicative structures in double co-chain complex. And again, this theory has, it can be formulated for upper indices or for lower indices, for decreasing differentials or increasing ones. Now I prefer to use with gradient increasing differentials, since main applications are for cohomology. So at the moment I prefer to consider these gradient increasing differentials. However, it is not important. The same theory is with gradient decreasing differentials, but now it is more natural to be in this situation. Okay, and what we assume? We assume that, well, what is a differential ring? Usual situation for introducing multiplication in some cohomology, in some chain complexes, we have a chain or co-chain complex, and we have multiplication in it which satisfies the Leibniz rule. Well, here the same. We would like to have multiplication, of course bigraded multiplication, so that mu, if we multiply an element in dpq with an element on dst, then we get into dp plus s, q plus t. And this multiplication, well, I will never use mu for it. I just say that a times b goes to ab. Well, and what this multiplication should satisfy the Leibniz rule. Leibniz rule means that but now we have two differentials, and we assume that we have Leibniz rule with any of them. So with each of them, delta prime satisfies Leibniz rule. Well, here we again have question about signs. My sign convention with delta 1, delta 2 anti-commutant corresponds to the following, that the main gradient for us is the total gradient, the sum of gradients. And so here we also need to, when we apply delta prime to B, we need to have -1 in the total gradient of A. So the modulo R is total gradient, so it's sum of the two gradients. And the same for delta 2 primes. Delta 2 prime of R times B okay. So assume that we have this situation. We will see that this is actually important situation, and we will see examples somewhat later today. But now, for a moment, assume that these are given data. So we have a double complex, which is a bigraded differential ring with each of the two differentials. Then, again, well, total of D is the differential ring with respect to the total differential. Total differential is just delta prime plus delta 2 primes, and once any of them satisfies the Leibniz rule, of course the total one also satisfies the Leibniz rule. So when differential satisfies the Leibniz rule, we have well-defined multiplication in cohomology. So cohomology of the double complex is in fact a ring. So we have cohomology of total complex is a graded ring, as usually when we have multiplication satisfying Leibniz rules in the chain complex. But our groups now our groups start. Oh, well, I change all notation. This goes from lower indices to upper indices. So when I am interested in such groups, well, I recall that in this situation they are cohomology of with respect to delta 2 primes. And once more, delta 2 primes satisfy the Leibniz rule. So this Z1 star star is a bigraded ring. A bigraded a bigraded ring. Then the first differential, D1, is induced by delta prime. By delta prime. And so it again satisfies the Leibniz rule, since delta prime satisfies Leibniz rule. So we have again some ring with differential. Oh, sorry, it's not Z, I'm sorry, it's E. It's the first term of the spectral sequence. We again have a ring with differential which satisfies Leibniz rule. Hence its homology, which is E2, again has good multiplication. Again is a bigraded ring. Actually, and so on. But we need to prove this. The fact is that so let us formulate the theorem. theorem is that every term ER of our spectral sequence is a bigraded ring and actually not just a bigraded ring, it is a bigraded ring with respect to the multiplication which is induced by the initial multiplication. Multiplication is induced by the initial. And each dr satisfies the Leibniz rule with that signs, as it's written there, satisfies the Leibniz rule, and so multiplication in term ER induces multiplication in term ER plus 1.
Sorry, what does it mean that multiplication is induced?
When we have Cochain complex with the differential, and differential satisfies the Leibniz rule, then multiplication in this Cochain complex induces multiplication in cohomology. In usual way, multiplication by two of two cycles, cocycles is a cocycle, multiplication of cocycle with a coboundary is a coboundary, and so we have induced multiplication. And here we are just in this situation that R plus first term is cohomology of the rth term with respect to differential, and if we know that differential satisfies the Leibniz rule, then we get the induced multiplication in R plus first term. And then we again have no new differential satisfying the Leibniz rule, and so on. That's yes, and also another claim is that the multiplication in the final term is associated with the multiplication with the multiplication in cohomology of the total complex, but let us discuss earlier what does it mean, this associated. Let us return. We later return to this question. Well, actually, the situation is even simpler. I recall that we have such sequence of groups. These are subgroups of DPQ. And we have such sequence of groups. Oh, I always have problems with writing indices in their proper places. B1, PQ. Okay?
Sorry, and in here, the infinity should be lower to...
Yeah, sure. Either everywhere lower or everywhere upper. Okay, we have these inclusions. But, and we have multiplication in the original complex D. Well, and these are subgroups in D, PQ. So actually, the claim which we will prove is as follows. So proposition, which immediately yields this theorem. Proposition, not immediately yields, but which clarifies this theorem very much. The proposition is that if we take two elements which are in ZR, So if we apply mu to an element in ZR with some gradients PQ, and another element in ZR with some gradients ST, then we always get into ZR again. So we have multiplication in this D, but it satisfies the following property, that the product of two elements, each of which is cycle of level R, is again cycle of level R. And the product of a cycle of level R with a boundary of level R is a boundary of level R. This is exactly, and in the opposite order the same. I just don't want to write it down. This is exactly, now actually we do not need to follow in such a recursive way to understand the multiplication in terms of spectral sequence. They are given just by this proposition. Once we know that the product of two cycles is a cycle, and if we vary one of these cycles by a boundary, then we get to a boundary. This immediately means that mu induces a well-defined product in the eth term of spectral sequence, in the rth term of the spectral sequence, and for each r, of course. And so actually we need to prove this first, this second, and this third, that dr satisfies the Leibniz rule. And that's all. That's the whole picture. And this is 4, of course. Well, so I suggest we have maybe 15 minutes break. Let us resume in 5 to 6. And then we discuss all these things. Что-то я не то нажал. So we need to prove these facts, and actually they are very easy. This is again some check which is more or less immediate. Let us do it. Well, I think I will check the first, and the second will be exercised. It is completely similar. For the first one, and also explain why it satisfies the Leibniz rule. We just need again to recall. We again need the definition of this group, and we again need those sequences. But now we have decreasing gradient decreasing differentials, so the sequences will be in the opposite order. Earlier they go left up, and now they go here, and differentials are not to below, and so the picture is as follows: delta 2 prime goes to 0, and here they sum up to 0 in all these cases. So this is the same picture, just transposed. Not transposed, well, not transposed by just we take symmetry with respect to the origin.
Is it Z or B?
Well, this is Z. Yes, the Z is set of y's for which there exist such sequences. Now I need two groups Z. I need to take the first element from Z and the second element from Z. So this is the first one, and I take the second one. This is again group Z, but with different indices. This is PQ, and that is ST. And again we have similar Z1, Z2, and so on, ZR minus 1, and similar conditions that this goes to 0, and they sum up to 0 in all cases. Well, actually, it is convenient, and now I would like to multiply this y and z. So I would like to consider an element yz, and I would like to construct similar sequence for it. It is convenient to do this. It is convenient to rewrite these conditions in the following way. Actually, what how I can say this in more easier. I can say that if I apply the total differential to this sum y, I will write here 0 just to for convenience. So if I apply it to the sum of all r's, then what I get? I get some element here. All other cancel. It is important for me that I get some element, let it be, well, A. But it is important for me that it is here. So the condition is that it is A which lies in this box. I don't know to compute complete coordinates. And similarly here, if I take the total differential of z0 plus etc. plus zr minus 1, then I have B which lies here. Yes? What I can say? I know that these differentials delta prime and delta 2 primes satisfy the Leibniz rule. And so their sum, of course, also satisfies the same rule. So I would like to consider the following element. I would like to consider the element y0 plus etc. plus yr minus 1. And I would like to multiply it by z0 plus etc. plus zr minus 1. First of all, where does this element lie? Its initial term is exactly y0, z0 as we are interested in. Here is the second term, y0, z1 plus y1, z0. This is just because they're in is bigraded. So just these gradients go to there. Here we have y0, z2 plus y1, z1 plus y2, z0, and so on. Well, what can we say about, but now this sequence is not of length r, but of length almost 2r. Well, but so the first glance is that maybe we get to z2r, but it is not true. The matter is that this condition is satisfied only up to step r. And let us check this. What we see here, let us apply here delta prime plus delta 2 primes to the whole product. Using the Leibniz rule, we see the following. Well, let n be the degree of y, the total degree of y. Just I needed to have, it is the same for all yi's, the total degree. I just needed, it will appear as such.
P plus Q?
Yes, that's P plus Q. Just I need this sign here. So first I can apply this to here, and then I get this A multiplied by Z0 plus ZR minus 1. Okay. But then I have another term. It is minus 1 to the power n, the degree of this. And I apply differential to here. I have y plus y r minus 1 multiplied by b. Now look where these elements lie, to which gradients they belong. Somewhere on this way we have the r minus, well, this is 0th, and I would like to consider r plus first step. y0 z r plus r minus 1 plus etc. plus y r minus 1 z0. And well, so that we have r boxes here. We have this sequence further, of course. But now look, if we multiply A, if we go from here to A, it is P steps right and or R steps right and R minus 1 steps down. So if we multiply Z0 by A, it is from here exactly this box. R steps right and R minus 1. So this first term A Z0 lies here. And similarly, Y0B also lies here. Further terms lie here, here, and so on. So our condition that this is 0, these two sum up to 0, these two sum up to 0, it is not true starting from here. If this were 0, then it would be true everywhere. But it is not 0, but it is not 0 only starting from here. So up to the till this point, we have our condition. And so we have the required sequence of R boxes. There are R of them up to here. Further, our rule destroys, and we cannot use it. But this is exactly what we need. well, this is the first moment, and now also we can see that we have also proved Leibniz rule for dr. Look, the matter is that this R A is exactly dr of y by definition. We have defined differential just it is a transpose situation because now, but we have defined differential just in this way, that we take this sequence and apply the last differential. And similarly, this B is exactly dr of z. So look, here this element goes to, we need to see the entry of this, which is here. And this is exactly a z0 plus minus 1 to the power n y0b as required. So this exactly implies Leibniz rule for one moment. This is not the result of this, but this is the result of summation of this and this. But as again, this is the image of delta 2 primes, image of delta 2 prime is B1, and so it is unimportant. We take the quotient by it. So we checked this, and immediately we checked this. This is exercise. And now let us discuss the relationship between multiplication in the limit page. Now we have already, up to this exercise, we have already checked that we have well-defined multiplication through the whole spectral sequence. In each term of spectral sequence, we have well-defined multiplication. Differential satisfies the Leibniz rule, and taking quotient by it, we get multiplication in the next term, and so very good situation. Now, what about multiplication in the final term? Let us first recall the relationship between so when we worked with gradient decreasing differentials, then our filtration was those which lies on the left from some line. When we reverse the gradient, our filtration is what those which lies to the right of some line. So we are now in this situation, we need to introduce the filtration FST in H, S plus T of the total complex of our bicomplex. It is by definition those elements which have representatives that lie here, that lie in hemiplane P greater than or equal to S, so that they have zeros here. And what we see that and again, if we take FST quotient by the previous one, and previous one now has numbers S plus 1, T minus 1, then this is exactly E infinity ST. Oh, sorry. Well, again, ST is here, infinity is here. And as in homological case, but just this. And the mapping from here to here, taking the quotient, is just taking this entry. Among all these, we recall only this one. Look, when we, if one cycle is represented by such y, y1, y2, etc. Now it's up to infinity. And the second is represented by similarly by z, z. Then their multiplication, as we have discussed just now, it starts from yz. And then something. So we see that the multiplication in these groups is the following. That if we multiply something filtration PQ and filtration ST, then we get interfiltration P plus S, Q plus T. And so when we get quotient, then if we multiply, I want to say that multiplication in these filtrations carries more information than multiplication in associated graded group. But multiplication here isn't used by multiplication here, but not vice versa. That's exactly the formulation of that theorem. That multiplication in E infinity term is induced by multiplication in this cohomology, in this filtration, but not vice versa. In general, we cannot restore multiplication here from multiplication there. Okay. Now that's general theory for any double complex. Now we consider Hochschild-Serre spectral sequence. We take one very important double complex, one particular very important double complex, and we see how does it works. So I want to erase all this general stuff, and we consider very particular example. And then we apply it to pure braid group, and we see that after all this theory is constructed, our proof is not our proof, but Arnold's proof is just straightforward. Well, so let us discuss. It is called Hochschild-Serre spectral sequence. We start from a short exact sequence of groups. So group G has normal subgroup H, and the quotient is Q. And we need to introduce projective resolutions. We need to have two projective resolutions. A projective resolution for, well, F star will be projective resolution for Z over ZG. So projective resolution for G. Projective resolutions for Z over ZG. So it's sequence of projective modules. And it is included in exact, all these modules are projective and the sequence is exact. Similar, and we need projective resolutions similar projective resolutions for Q. So P star will be a projective resolution for Z over ZQ. Okay. Why we do not need a projective resolution over H? We have three groups. The matter is, first of all, well, one note that actually we always can take free resolution. It is projective, but actually, if we need, we always can take free resolutions. For instance, bar resolution. Well, we do not need another resolution for H, since F also works over H. If F, Q are free ZG modules, then they are free ZH modules, of course. This is an important note. If FQ is a free ZG module, then it means that what does it mean? It means that it has some basis, yes? And it is just a module of all formal linear combinations of elements of some basis E lambda. Well, with coefficients in ZG. But then I can consider F over ring ZH. Well, okay, any element of G is obtained as we can take some representatives. We can take some representatives of left cosets over H. Say, let G1H, G2H, etc. be all different left cosets. Then, no, vice versa. I want right cosets. I'm sorry. Then, if I take Gi E lambda, then it is a basis of this module over ZH. Since any element can be uniquely written as some element of H multiplied by one of these representatives. So if this is a free basis over ZG, then this is automatically a free basis over ZH. So we see that if a module was free over ZG, then it is also free over ZH.
Gi are all elements of G, or?
No. Represent, these are all right cosets. We take one element in each right coset.
Okay.
So all right cosets. Then it is free basis of ZH. Good exercise. I don't want to spend time for it. We can always take free, but actually the same is true for projective modules. This is an exercise that a projective module over ZG is always projective over ZH. So actually over H we have the same resolution. So we do not need any additional resolution. Now, now the following, this is almost what we need, but we also need some G module. So suppose that our goal is to compute homology or cohomology of the group G with coefficients in M. This is what we want. We want to introduce some spectral sequence which computes this homology or cohomology. I would like to recall that we can look, this is G module and this is G module. But we can consider their tensor product not over G but over H. What it is? By definition, it means that we take their tensor product just over Z as abelian groups, and then we take coinvariance. This is just the definition of tensor product over ZH. That we take the quotient of this tensor product by simultaneous multiplication by elements of H. Well, so what is coinvariance? Coinvariance is just quotient by the action of H. Yes? If we are in such situation that some a group G acts on something, on any set, and we take quotient not by the whole group but by the subgroup H, then the quotient group will act on the orbit set. This is general mathematical situation, that if a group acts on something and we take a quotient of subgroup, then the quotient group acts on the orbits by a subgroup. This means that these are Q modules. Well, and now I can write down double complex, which we start from. This double complex is as follows. This is just double complex of abelian groups. dpq is, we take this resolution for Z over ZQ, and we take tensor product over Q with this Q module. Well, so that's our double complex. Why it is double complex? We have differential here, and we have differential here. And so our differential in F induces differential. Actually, not only these are Q modules, but if we take the whole F star tensor M and coinvariance over H, this is a chain complex of Q modules. So is a chain complex of Q modules. And so once we have one chain complex and another one chain complex and another chain complex, then we have two differentials on their tensor product, namely d prime of, if A is from here and B is from here, then d prime of A tensor B is dA tensor B, where D is differential in this P. And the 2 primes of A tensor B, okay, to obtain our sign convention that they anti-commute, I must write down here -1 to the power P. And here A times dB, where D is differential in this chain complex. I'm sorry. If I try to denote differentials by different letters, it will be very cumbersome. But this is differential in P, and this is differential in F star tensor over with M over H. So we have this double complex, and we can start studying the spectral sequence as we constructed in the previous part of the lecture. Let us look what can we say about the corresponding spectral sequence. Well, let us start with the term E1. What can we say about the term E1? Look, by definition, this is homology of this double complex with respect to this differential D2 primes. Now, look, what is the differentials of this chain complex with respect to D2 prime? I recall that if we would like to compute the homology of this chain complex, I take F star and I take tensor product with M over H, then this is just by definition the Qth homology of the group H with coefficients in M. Well, we take projective of free resolution for H, we tensor it with some module M, and we compute the homology. This was just the definition of homology groups of H with coefficients in M. Now, what we are interested in is not completely this, but it is this tensored by some group P. Look, this group, now we compute homologies of columns of our complex. Over column, this P, this group is fixed. If we consider Pth column, then we have one and the same group P over in all these entries. And moreover, this is a projective, or we can assume that even free Q module. Generally, tensor product is not an exact functor, but tensor product with free module is, of course, an exact functor. So, what we get is exactly the tensor product of this homology with that Q module. So, we immediately see that this is the Pth homology. So sorry, why not the we have Qth homology, but we have P index P over Q by Qth homology of H with coefficients in M. Well, that is exactly our result. Now, this was first step. We took the homology along this line. Now we have how the second term of the spectral sequence arises. We take the quotient of this by D1. And I recall that D1 is induced by D prime. And D prime is just the differential in this P. So D1 is exactly given by differential here. So now, look, we have now Q is fixed, and D1 acts in this direction. And now we again are in the same situation. We have free or projective resolution, now for the group Q, and we take the homology of this projective resolution tensored by such Q module. Well, this is by definition. The E2 PQ is by definition cohomology of E1 with respect to D1, and it is by definition the homology of this row, and it is by definition the pth homology of the group Q, since it's a resolution for Q, with coefficients in this Q module. So what we get? In this situation, the description of E1 is not so convenient. It depends on some choice of projective resolution and so on. But the term E2 is independent on any choices of resolutions. It is written completely in terms of homology and this is again exactly what we need. We need to obtain some information from homology of G, starting from homology of H and Q. And it turns out that the term E2 is obtained exactly in this way. We take pth homology of Q with coefficients in qth homology of H. Here it is important that since all these were Q modules, as we discussed, these are also Q modules. So these are homology with twisted coefficients for Q. Even if M was module with trivial action of G, it can the action of Q on this homology can be non-trivial even in this case. Okay, so we understand the term E2 very good. But, well, now what is our goal? Our goal was to understand the homology of G. But up to now, this has nothing with homology of G. We know that our spectral sequence converges to something which is related to homology of the total complex of this double complex. So this spectral sequence converges to some term E infinity. Then we have several differentials. They are usually complicated to describe explicitly, but we know their degrees and we can extract some information from there. But it goes to E infinity, which is associated with some filtration. But some filtration where? In homology of the total complex, total complex of this double complex D. Let us understand that the claim is that this is exactly homology of G with coefficients in M. But of course we need to prove this. Well, and the proof is as follows. I would like to recall that there are two spectral sequences associated to a double complex. And now let us consider another one. So we take the same double complex as before, but we reverse the roles of D prime and D2 prime. So I will denote it by such calligraphic E. EPQR is the second spectral sequence. The second spectral sequence associated with D. This means that we reverse the roles of D prime and of D prime and D2 primes, and we reverse the orders of two gradients, the roles of two gradients. What does it mean? First, this means that the first term of this spectral sequence, the first term, is just the homology of our double complex with differential d prime. Well, and then the first differential is induced vice versa by d2 primes. Induced by d2 primes, and generally let us I denoted by delta. I would like to distinguish between differentials of this spectral sequence and actually the degree, the by degree of the differential delta R in usual homological spectral sequence, it has by degree in usual homological spectral sequence, the dr acts by minus r minus 1. Okay? And here the roles are vice versa, so the roles are swapped, so these by degrees r minus 1 minus r. So this is very unnatural to consider spectral sequences and such, but still, okay, let us start. And again, E infinity is associated with some filtration in the total complex. Okay, let us start studying this spectral sequence. What can we say about E1? Look, E1 is differential of this double complex with respect to the first gradient. I claim that this differential, this homology is trivial unless let us write down it more explicitly. We take the differential or the homology of this double complex with respect to this gradient. So we take a projective resolution of P, tensor it by such module, and compute the homology. This is homology of Q. By definition, this is pth homology of Q with coefficients in this module. I claim that this is 0 unless P equals 0. So if P is not 0, then this vanishes. Let us understand why this is so. We need some information about this module. Look, for simplicity, let's assume that F is free. If F is free, then this modules is just sum of identical pieces. Identical pieces are the module ZG, but considered as left H module, and tensor product with M. So actually we need to prove the following, that I claim that HP of Q with coefficients in such a module is 0 for P not equal to 0. Why this is true? Look, how does this module looks like? We need to take the tensor product of these two H modules and we need to take coinvariance over H. Well, for a moment, let us write down another module. Let us consider the module M0, which is the same abelian group as M, but with trivial action of H. So M0 is M with trivial action of H. We have some action of H here, but we artificially consider the same module with trivial action. We can consider similar coinvariants. These are different coinvariants. Here we the action is on both, but here only on the first. I claim that this is isomorphic. Moreover, it is isomorphic as Q modules. Well, why? Well, because we can just write down this isomorphism explicitly. If we have here some element Xi and here some element M, well, if we have Xi tensor M here, then we need to take it to sorry, one moment. If we take G over M, G is an element of a group, then we needed to take here by well, if we have G tensor M here, then we needed to take to G tensor GM there. Then the action from the left goes to the action on the left. So we have this isomorphism. Why it is? But now these coinvariants. Now the action of G is only here. So this is the same as coinvariance of the G tensor M0. But this is exactly the group Rien for Q. So this is ZQ tensor M0. This tensor is just over Z. This is just tensor product of abelian groups. So we see what we see. We see that this module, this is called an induced module. This module is induced Q module. What does it mean? It means that we have an abelian group and we tensor it over Z with free Q module. Such modules are called induced. We take free. Here just one-dimensional free, but if we return to here, then it will be several such summands. So we have tensor product of free module, tensor product just as abelian groups over some abelian group without any action of Q. Such modules are called induced, and it is a good exercise that homology with coefficients in induced module are always trivial in dimension. So it is a good exercise that if N is an induced Q module, which is by definition, so it means that N is product of the tensor product over Z of ZQ with I just don't write with Z with some abelian group. Well, then homology of Q with coefficients in N are 0 in dimensions not equal to 0. So what we get? We get that our term E1 lives only in one column. We have only one column P equals 0. And in this column, concerning zeroth homology, we know very well that it is just always coinvariance of the module. This is general fact, this is always coinvariance. So this one, if we take 0q, everywhere else it's 0, but if we take 0q, then we have, it is just naturally isomorphic to, canonically isomorphic to fq times h with m and coinvariance over q. Well, but now what is this? Look, this was a module over G. This also was a module over G. We took their tensor product over H. This means that we took their tensor product as abelian groups, and then we take quotient by H. And we said, okay, now it became Q module. But now we take quotient by Q. So if we first take quotient by the action of a subgroup and then over factor quotient group, then it is the same as taking quotient by the whole group at once. So this is exactly FQ, tensor product over G with M. And now we have differential delta 1, which goes here, and which is induced by differential in FQ, since it is induced by D2 primes. So now we know E2 PQ is homology of this with respect to the differential. And again, by definition, we see that, well, of course, again, we have, it is non-trivial only in first grade, it must be 0, otherwise it is just 0. And if it is 0, then we have here the qth homology of G with coefficients in M. Well, but now, okay, so this is the second term, but I claim that this is the limit term as well. Why? Because all other, we have only one column, and all other differentials are trivial just by dimensional reasons. They are trivial by dimensional reasons. And so, what we see? We see that this is limit term. Moreover, look, in general situations, we know that groups on the diagonal are consecutive quotients of some filtration in homology group. But now we have only one group on each diagonal. So a priori we know anything about, we know nothing about the filtration. But since we have only one group, then it must be isomorphic to the corresponding homology group. So we actually see that this limit term is isomorphic to the homology group of that total complex. So we arrive to the situation that this is exactly the 0q. The qth homology of total complex of D. Well, that's again exactly what we need. The qth homology, the homology of this total complex is isomorphic to the homology of group G with coefficients in M. And now E infinity term of the first, now we can forget about that second spectral sequence, actually it is very auxiliary. It just is needed to understand that the homology of the total complex are isomorphic to homology of G with coefficients in M. Now, starting from that point, we forget about that second spectral sequence and return to the first one. And what we see? We see that we have term E2. Term E1 never is interesting for this spectral sequence, almost never. Actually, there is only one reason why we need to consider E1. If we want to compute differentials, then we need to work in the total complex itself. And not even in E1, but in the total complex D. But if we just would like to apply standard machinery of spectral sequences without explicitly computing differentials, then one usually starts from E2, which is written just in this way. And now we need to take quotients by several differentials, and we arrive to something which is associated with a filtration in the homology of group G. And this is called Hochschild-Serre spectral sequence. Of course, it has variant in cohomology. All the story is directly the same. And so I only would like to formulate the results without further explanation. So in cohomology, we need to start with complex. Well, prefer to look. Oh. Yes, that's instead of tensor product, we need to use Holmes. Again, P is resolution for Q and F is a resolution for H, and we need to take this double complex, and the result is that we know the second term of the spectral sequence. Again, now it is cohomology of P or of Q with coefficients in Q's cohomology of H with coefficients in M. And E infinity PQ is associated with certain filtration in cohomology of G with coefficients in M. Well, what is important in the case of cohomology? Again, there exists one situation when this case is richer than the case of homology. This is multiplication. To see multiplication, the easiest situation when there is multiplication, and I want to consider only this one. I don't want to work with multiplication with twisted coefficients. So, first of all, this is general situation, but now assume that here is some ring. So first of all, this is a ring, and this is a ring with trivial action of G. So we have an untwisted coefficient with trivial action of G. So we have here the same things. And also we assume that Q acts trivially on this cohomology group. I would like to have untwisted coefficients here too. So Q acts trivially on H star of HR. This is assumption. There is no reasons for this in general situation, but assume that it is true. Well, I recall that once we have a coefficients in a ring and it is untwisted, then we can use approximation of diagonal in F to construct multiplication in such cochain complex of this complex of cochains for the group H or for any group. Okay, if we have untwisted coefficients which form a ring, then we get multiplication in this cochain complex, which satisfies Leibniz rule, and so we have good multiplication in cohomology. And here we twice in this situation. First of all, we consider, first of all, here we have multiplication in this cochain complex. And second, we again have from P to a ring. Now we have multiplication here, so this also becomes a ring. And we have coefficients, we have home from P to some ring, so over Q, so it again becomes we again have multiplication. So this actually becomes a bigraded ring, and we are exactly in the situation we discussed. Just one note that, of course, multiplication in cohomology is always associative. Multiplication in cochains generally is not always associative. It was associative for particular choice of approximation of diagonal in bar resolution, but generally it is not associative. But to construct multiplication in spectral sequence, we never use associativity, so we just do not need it. So it works for any approximation of diagonal. So what we see? We see this general situation that each term is a bigraded ring. Each differential satisfies Leibniz rule, and the multiplication in final term is associated with with the multiplication in the homology. This is just direct consequence of general situation. Well, so that's all about general facts about this Hochschild spectral sequence. But now let us apply it to pure braid group from which we have started. Okay. What we see? We have this particular split short exact sequence, which we have already discussed it several times. This is pure braid group. This is forgetting the last strand, and this is how the last strand goes around the first n-1. This is free group. Now let us apply Hochschild-Serre spectral sequence in this particular situation. What we see, for coefficient ring, I just take Z with trivial action. So Z, coefficients in Z. Well, what can we write down? Let us write down the second, and I prefer to work in cohomology. Let us write down the second term of this spectral sequence. So this is HP of Q. Q is this group with coefficients in HQ of the free group. Okay? But then, yes, here the coefficients is Z, so I don't want to write it. Okay, let it be Z. Okay. What we know about these coefficients? This is cohomology of a free group. We know very well that for a free group, its resolution is very short. And actually, this is the same as cohomology of wedge of circles. And of course, we have zero cohomology unless Q is 0 or 1. In these particular situations, first of all, zero cohomology of this group with coefficients in Z, of course, is Z. And action is trivial. Well, what is about first cohomology? First cohomology of this group with coefficients in Z is, again, by definition, is just homomorphism from this group to Z. Well, and I recall that we have constructed such homomorphisms. These are just, this is isomorphic to Z to the power n minus 1. And this is generated by those homomorphisms omega k n, where the last one is n, so the nth strand goes along this. With 1 less than or equal to k, less than or equal to n minus 1. And of course, the action of this pure braid group on this cohomology is trivial. The matter is that conjugation by an element of braid or pure braid group doesn't affect these homomorphisms. This is just counting homomorphisms of certain generators. So we are exactly in this situation, and it is important that we have a multiplication here. And what we see, our spectral sequence, lives only in two rows, 0th row and first row. So our spectral sequence consists of two rows. This is Q equals 0, and this is Q equals 1. Well, and now what we see, we obtain that the 0th row is just the cohomology of pure braid group Pn minus 1 with coefficients in Z. So here we have just cohomology of Pn minus 1 with coefficients in Z. And the first row is cohomology, So here we have HP, cohomology of Pn minus 1 with coefficients in home from Fn minus 1 to Z. Well, and in particular, I am interested in this group. What is this group? This group is the zeroth cohomology of Pn minus 1 in this home. What is zeroth cohomology? Zeroth cohomology is just invariance of this home, but we know that the action is trivial, so this is just this home itself, which is, well, I prefer to write down that it is n minus, first cohomology of Fn minus 1. Well, okay, by induction we know this one. I recall that this is free exterior algebra generated by omega k L with 1 less than k less or equal less than L less or equal to n minus 1, quotient by some relations which we know explicitly, omega kl omega lm plus omega lm omega mk plus omega mk omega kl equals 0. And we know this one. This is generated by dimensional reasons. There could be one differential. There could be differential d2. So a priori we do not know anything about it, but I claim that we know something about this particular differential. Well, why? Because I claim that this one is 0. The matter is that, look, suppose that it was not 0. Then the next term, and it would be the final term, would be some subgroup of this one, some proper subgroup, kernel of this. And but look, this first, what is the meaning of this subgroup? In this situation, this diagonal corresponds to the first cohomology of the whole pure braid group. This group is embedded into, this group is embedded in this cohomology, and this is the quotient. So actually, the group which is here is exactly the image of pullback. So the group which stands here at the end, E infinity 0, 1, is exactly this map from cohomology of this group to cohomology of that group is induced by I. So this is exactly the image of I star from the first cohomology of Pn to the first cohomology of Fn minus 1. But what about the first cohomology? We have computed it in both cases. We have road presentation, and we know the homes from these groups to Z, and it is easy to see that it is surjective. So this must be the whole group, and so these differentials must be 0. But now, in each group like that, this group is always tensor product of that and that. This is just cohomology with coefficients here, so it is by it is just tensor. And so this is 0 by Leibniz rule. So this is the typical example how multiplicative structure works. It is rather hard to check this for any step, but we checked that it is 0 in this step, and now we use Leibniz rule. So all differentials are 0, and now I think I need to stop, but now it more or less follows. At least we immediately see that we have proper ranks, and everything is generated by omega KLs, and that's already implies that that's all. Since if we take quotient by such relations, then we just have those rank which we want to consider. Okay, so I think I stop here. I only want to suggest you one very useful exercise to consider the first case when there is a non-trivial differential. The first case is the following. There is so-called Heisenberg group. Let us consider unitriangular 3x3 matrices with integral entries. This group is not commutative, but it has a commutative subgroup. Well, which of them is commutative? If we have just matrices of such form, then they form a commutative subgroup, and the quotient is also commutative. So we have a short exact sequence. Well, the kernel is Z, this Z. Then we have this Heisenberg group. And then we have Z squared. The quotient is, of course, the squared. And the exercise is to consider Hochschild-Zeller spectral sequence for this extension and to compute the cohomology ring. So consider the Hochschild-Zeller spectral sequence for this extension and compute. Of course, we know cohomology of this sum and compute the cohomology of Heisenberg groups. Well, okay, that's all for today.